Welcome back. This is topic 27, feed-forward and backpropagation. We can already build a network, and we know why its activations matter. Today, we reach the heart of the matter, how a network actually learns. Forward to predict, backward to learn. 4 parts. First, the 4-step cycle that every round of training follows. Second, the one rule from calculus that all of learning rests on, the chain rule. Third, 2 work examples we grind out entirely by hand. And fourth, a short quiz to try yourself. Training is a single cycle, repeated thousands of times, always in the same order. Step 1 is feed forward. The input flows forward through the network, layer by layer, until the output produces its prediction, y hat. Step 2 is the loss. Compare the prediction y hat with the true target y, and collapse the difference into a single error number. Step 3 is backpropagation. The error now flows backward through the network, handing every weight its own gradient, the partial derivative of the loss with respect to that weight. Step 4 is the update. Gradient descent nudges every weight a little way downhill. The new weight is the old weight minus the learning rate times its gradient. 4 steps, 1 order every single time. If you remember nothing else, remember this: forward to predict, backward to learn. Look closer at that first step. A network computes its prediction the only way it can, layer by layer, front to back. Each layer forms a weighted sum plus a bias, that is the pre-activation Z, and then applies its activation phi to get the output A that it passes on. Information flows strictly forward, never sideways or back. Only on the tiny network we will use all topic. 1 input, 1 sigmoid, hidden neuron, 1 sigmoid, output neuron. The input one becomes Z1 of 0.5. The sigmoid turns that into a hidden value of 0.6225. The second weight turns that into C2 of 0.3112, and the final sigmoid gives a prediction of 0.5772. 2 things to hold on to. The forward pass stores every intermediate value because the backward pass will need all of them. And forward alone only predicts. To learn, we still need a gradient for every weight. Let us actually compute that forward pass with nothing but a sigmoid table. Start at the input x equals 1 with the first weight 0.5. The pre-activation Z1 is the weight times the input, 0.5 times 1, which is 0.5. Push the 1 through the sigmoid. Since either the minus 0.5 is about 0.6065, the hidden value is 1 over 1 plus that, which comes out to 0.6225. The output neuron reads the hidden value with its own weight, also 0.5. So Z2 is 0.5 times 0.6225, which is 0.3112. One last sigmoid. More hat is the sigmoid of 0.3112, which is 1 over 1 plus 0.7326, giving 0.5772. 4 little steps, 4 stored numbers. Z1, the hidden value, Z2, and Y hat. Keep all 4 on the table, because the backward pass is about to reach for every one of them. Now, the rule that makes the backward pass possible, if Z depends on Y and Y depends on X, then the derivative of Z with respect to X is the product of the two local derivatives along the way. That is the whole chain rule. Say it in words, because we will lean on it constantly. A derivative through a chain of steps is just the product of the derivative at each step. Take the example apart slowly. Let's be squared, where the inner function y is 3x squared plus 2x plus 1. At x equals 1, the inner value is 3 plus 2 plus 1, which is 6. The outer derivative, treating y as the variable, is 2y. At y equals 6, that is 2 times 6, which is 12. The inner derivative is 6x plus 2. At x equals 1, that is 6 plus 2, which is 8. The chain rule multiplies the two local slopes together. 12 times 8, which is 96. Two local slopes, one product. That is all the chain rule ever does, and backpropagation is this same move repeated once per layer. Here is why that matters for a network. A network is exactly such a chain of compositions. A weight sets the pre-activation, which sets the output y hat, which sets the loss L. So the gradient we want, the partial of the loss with respect to the weight, is a product of three local derivatives. Forward stores each value. Backward multiplies those local derivatives, right to left. Let us read that product one factor at a time. With the weight, which is the loss through a chain, it sets y hat, which sets the loss. So its gradient is the product of three local slopes. The first factor, the partial of the loss with respect to y hat, is how much the loss reacts to the prediction. The second factor, the partial of jack with respect to z, is the activation's own slope, sigma prime of z. The third factor, the partial of z with respect to the weight, is just the input feeding that weight. Multiply the three together and you have the gradient. The entire backward pass is nothing more than reading this product, right to left. Time for a full worked example. One sigmoid neuron, weight 0.8, bias 0.1, input 0.5, target 1. Forward gives a prediction of 0.6225 and a loss of 0.0713. The three local derivatives multiply to negative 0.0444 and one step with learning rate 0.1 moves the weight to 0.8044. The handy shorthand is delta, the error signal at the neuron. Let's derive every one of those numbers ourselves. The neuron, weight is 0.8, bias 0.1, input 0.5, target 1, and squared error loss. First, the pre-activation Z is the weight times the input plus the bias. 0.8 times 0.5 plus 0.1, which is 0.5. Through the sigmoid, the prediction you had is the sigmoid of 0.5, which is 0.6225, and the loss it earns against the target one is 1/2 times the difference squared. The difference is negative 0.3775, and 1/2 of its square is 0.0713. Three numbers now stored. Z is 0.5, Y hat is 0.6225, and the loss is 0.0713. Now walk them backward. Multiply the three local derivatives right left. The first, how the loss reacts to the prediction is V hat minus V, which is 0.6225 minus 1, negative 0.3775. The second is the activation slope. Sigmoid prime of D is sigmoid times 1 minus sigmoid 0.6225 times 0.3775, which is 0.235. And the third is the input feeding the weight, which is just x, 0.5. Now multiply the first two. Negative 0.3775 times 0.235, which is negative 0.0887. Then take that times 0.5, and the gradient is negative 0.0444. Take 1, gradient descent step with learning rate 0.1. The new weight is 0.8 minus 0.1 times negative 0.0444, which is 0.8044. The weight moved up, pushing the prediction toward the target. The bias trains exactly the same way, only its last factor changes, because the partial of that with respect to the bias is 1 instead of the input. That makes its gradient negative 0.0887, so the bias moves to 0.1089. The real power shows with a hidden layer, because now the error has to travel further. Here is the picture. An output neuron's error is propagated back through the connecting weight into the hidden layer. Let us make that concrete. Two neurons in a line now. Input 1, a hidden neuron with weight 0.5 and bias 0, feeding an output neuron with weight 0.5 and bias 0, both sigmoid, target 1. First layer, Z1 is the weight times the input, 0.5, and the hidden value is the sigmoid of that, 0.6225. Second layer, Z2 is the output weight times the hidden value, 0.5 times 0.6225, which is 0.3112. The prediction E, that is the sigmoid of 0.3112, which is 0.5772. And the loss is 1/2 times the difference from 1 squared, which comes to 0.089. It is the same forward pass as before, just one layer longer. Every value is stored, and the backward pass will start at y hat, and work left. Now the backward pass on this network. Start at the output neuron. Its error signal delta 2 is the prediction error times the activation slope, which is negative 0.103. The gradient for the output weight is that error signal times the hidden value, negative 0.064. Here is the crucial step, propagation. To learn how the loss depends on the hidden output, push the error signal back through the connecting weight. The partial of the loss with respect to the hidden value is delta 2 times the output weight, negative 0.052. From there, the hidden neuron follows the very same pattern. Its error signal delta 1 is that propagated error times the hidden activation slope, negative 0.012. And the gradient for the hidden weight is delta 1 times the input. Again, negative 0.012. That is the entire idea of a backpropagation in one sentence. The error at a layer is the error at the next layer passed back through the weights that connect them. Let us name the recipe because everything backward reduces to it. Define a neuron's error signal, delta, as the error arriving at that neuron times its own activation slope. Once you have delta, each weight's gradient is simply delta times whatever that weight reads as input. No new calculus, just a multiplication. And to reach the previous layer, you push delta back through the connecting weight. That is the propagation move. The partial of the loss with respect to the hidden value is delta 2 times the output weight. Check it on our numbers. The output error signal delta 2 was negative 0.103. Push it back through the weight and multiply by the hidden slope, and the hidden error signal delta 1 is negative 0.05, 2 times 0.235, which is negative 0.012. One recipe applied at every neuron from the output backward. Compute the error signal, read off each weight's gradient, push the signal back one weight, repeat. That is the whole backward pass. Let us state it in general. For every layer, the forward pass computes the pre-activation and the output and stores both. Step 2, the loss, compares the final output to the target. Step 3, the backward pass, computes the error signal at the output and then carries it back layer by layer, multiplying by the weights to move between layers and by the activation derivative at each neuron. Step 4, the update nudges every weight down its gradient. That is the algorithm, whatever the depth. And here is the happy ending. You never actually write these derivatives yourself. Deep learning libraries record every operation of the forward pass and run the backward pass for you. In PyTorch, this is autograd. So set requires grad to true, compute a result, call dot backward, and the gradients appear in x.grad. The printed gradient is 5.333 6.667. Let us confirm by hand that AutoGrad got it right, because it is running exactly this topic's algorithm. Read the code as mass. It builds v sub I equals x sub I plus 2, then z sub I equals 2 y sub I squared, and then averages the 3z values into the output. Differentiate one term. The average contributes 1/3, and the derivative of 2y squared with respect to x is 4y. So the partial of the output with respect to x sub I is 1/3 times 4y, which is 4/3 times y. With inputs 1, 2, 3, the inner values are 3, 4, 5. 4/3 times those is 4 16/3 and 20/3, which is 4 5.333 and 6.667. Exactly. The tensor for 5.333 6.667, the dot backward returned. The library ran this same chain rule for us, term by term. Now try it yourself. Same two examples with the fresh numbers. Please 1. A single neuron, weight 0.6, bias 0.2, input 1, target 1, learning rate 0.1. Run the forward pass for z, y hat, and the loss, then compute the 2 gradient and take one update step. Quiz 2, one hidden layer. Input 1 into a hidden neuron with weight 0.4 into an output neuron with weight 0.6, both sigmoid, target 1. Do the forward pass, then the output error signal its weight gradient, propagate back to the hidden value, and finish with the hidden error signal and its gradient. The full solutions are in the lecture note. Let us recap. Learning is a 4-step cycle. Feed forward, then loss, then backpropagation, then update. Feed forward computes the network layer by layer, front to back, and stores every intermediate value for the pass to come. Backpropagation is the chain rule made systematic. Multiply the local derivatives from the output back to each weight. The one move to remember is propagation, the error passed back through the connecting weights. And AutoGrad does all of it automatically every time you call loss.backward. Next topic, we put this to work in PyTorch itself. Building and training real networks and letting AutoGrad handle the calculus. See you there.